I thought I'd start the year off with a bit about astrophotography. There's kind of a lot of tech changes have been happening over the recent years where people that haven't got a lot of time to do what's quite a difficult exercise, sort of technology has come to the rescue in the form of what are called digital telescopes or EV scopes, sometimes they're called. Basically, it's a combination of a mount, telescope and camera all in one with all the bells and whistles software. You don't have to worry about things like polar alignment. They figure them all out itself. And the society have actually authorised Steve here to purchase one for rental stock. So, which one are we getting?
Yeah, the C-Star. I've not ordered it yet, but yeah.
Okay. So
S15.
that machine will be available for rental. Probably need a little bit of instruction more than the Dobsonians that we rent out, but it should let people to have an easy entry into this astrophotography.
Nice.
So I'm just going to show a few random pictures. This is actually one I took in 2007 using a point and shoot camera, and I had the camera sitting on the railing so that it wasn't moving around, set it for the maximum exposure that you could. And this camera had one advantage in the menu: you could turn on manual focusing.
Yeah.
Because in these conditions, a point and shoot camera wouldn't figure out that it was supposed to focus on the sky rather than those lights or whatever. So it doesn't take much gear to get started with this stuff. Really simple point and shoot camera. Well, these days, cell phones can be used to get started with this, and the cell phones will do much better than this. Anyone can tell me what that comet is?
2017?
2007.
Oh, I don't know.
I bet Steve knows. It's a Comet McNaught 2007 P1, 2006 P1, I think it was. So that was an actual naked eye comet that could be seen even in the twilight sky just with your eyes. We haven't had a comet that bright since, and we never know what's going to happen with these things. Okay, this is what I'm showing you here is that one with the comet is an example of a solar system object in a skyscape. So it's basically a wide angle image, and this is another one taken out at the Cumulus Observatory just with a DSLR, single longish exposure shot of the Milky Way rising over a tree. None of these, this is my stuff, not very good compositions, but it just shows you the sort of thing we're talking about. That was done with a DSLR camera. And another skyscape, but this is a different type of thing where it's actually a whole stack of images that are merged together. So there's two ways you can stack up them so that the stars actually will sit over the top of each other, and that's your normal sort of astrophotography. Or this type where there's no alignment, you just stack the top of the other, and you get what are called star trails. In the old days of film photography, you just take a super long exposure to do this sort of thing. If you try doing that with a digital camera, we'll turn it on bulb mode and take a 2-hour shot, all you get is basically a complete white image, because the actual data will be overrun by what's called thermal noise or dark current.
Yeah.
So you are limited how long an exposure you can take with a digital camera. However, if you chill them, they can last longer. So
Yes, whatever.
Depending on how cold you can cool your sensor.
It also shows the movement of the Earth quite nicely.
Yeah, so obviously the stars appear to be all circulating around the south celestial pole, which is right in the middle there. That town in the background is Whitianga. So another type of astrophotography get into purely planetary stuff with no terrestrial things in it. This picture of the moon was taken with a Dobsonian telescope. And with the moon, you can do this because it's so bright that you don't need to track the moon. You just take a short exposure, maybe a 400th of a second, depending on your ISO settings, that kind of thing. So the moon hasn't really moved even at a focal length. I think this was about, would have been 1200 millimeter focal length with the 8-inch Dobsonian. And again, that's just with a DSLR, but with instead of having a lens, you use an adapter to adapt it to the standard telescope 2-inch focusing. Okay, this is another solar system one. Now, this one was actually taken on the observatory telescope here upstairs on the Zeiss using a thing called a Flea 2 webcam. And the way this image was done, again, Saturn is quite a bit dimmer than the moon, but it's still not what you call long exposures. And this was done using basically taking a video. In other words, instead of a picture, it was a video of maybe 3 minutes long. And then what you do, you process the video, and the software takes all the good, what it considers to be good frames, stacks them together to cut down on the noise and bring out the detail of the image. Sorry?
Why black and white instead of colour?
The Flea camera was a black and white sensor.
Okay.
And that's why I did have some examples of color ones as well, but this was just the thing about this though is that when we were talking about those digital telescopes before, you won't be able to do this kind of image because you need a long focal length because Saturn is really tiny. So you could image it on a digital telescope, but it would only be a tiny thing in the frame.
What about Voyager 1?
Oh, those spacecraft get really close to the planet, so they have their, no, that's a good question. Because they're flying out there, they don't need a super long focal length or a big telescope because they're actually up close to the planets.
Okay.
Same with any of the space probes. And here's a much better shot than I could ever do. This was an image taken by Rolf Olsen, and this is a pure deep sky shot of a galaxy cluster. And you can see that red stuff there is actually foreground mission nebula in our own galaxy with several galaxies, as you can see in the background. I think his telescope for this it was basically a 12-inch Newtonian, but he's using a proper astro camera, dedicated camera, not a consumer camera. Okay, a bit of background history. So that's the kind of things you can do. You've got the skyscapes. I didn't have an example there, but Aurora is a great thing you can do with just a camera and lens. And we've had quite a good activity in the last year or so with that, with the sun putting on a bit of a display. Historically, astrophotography obviously started after the invention of film, and originally it was basically glass plates they used. And one of the first to experiment with astrophotography after the invention of photography was Henry Draper, who I believe was he a dentist or some sort of medical field anyway. And so he managed to image the Messier 42, which is the great nebula in Orion. And so that was the pioneering days. And he also was the first to try and get the spectra of stars. He was an amateur, but and he was pretty wealthy, and his widow gave a lot of money to Harvard University, and they did a big project imaging the whole sky from their observatory and also some observatories in the southern hemisphere. The glass plates from that actually still exist, and they've all been digitally scanned, and there's a lot of interesting information they can glean from them. But of course, photography, as we know, eventually got overtaken by digital sensors. First of all, the CCD, it was actually invented by Kodak, who kind of put themselves out of business. And then more recent times, particularly with consumer cameras, of your DSLRs, your mirrorless cameras and cell phones, they all use CMOS, which is a little bit similar technology, but CMOS is easier to produce because of computer chips use the same technology. It means they've got all the well-designed equipment for producing that kind of stuff. So they're a lot cheaper to produce than CCD. And so the different parts of astrophotography you've got to think about are cameras, the optics, the mounts, and the processing. And the digital scopes try to combine all this, so hopefully making it a bit easier. Just a quick overview of cameras. So as seen, you can use point and shoot type cameras, cell phones. A little bit tricky to use if you want to combine them with a telescope, but you can do that. You can get various holders and things that I don't know if anyone's here tried to take images through the Zeiss on a cell phone. It's actually quite difficult to position the camera in exactly the right spot.
I think Astronomy sells a
holder so you can adjust the thing and then once you've got it right, you can lock it in place. Yeah. And of course, you DSLRs, mirrorless cameras, you can get adapters. You have to get an adapter specific to your brand, whether it be Nikon, Canon, or Sony, that allow you to adapt your camera to a telescope focusing. And as mentioned before, the webcams are useful for bright objects, the sun, moon, and planets. Obviously, with the sun, you need a blocking filter. Generally, the solar system objects, the sun, moon, and planets, you're not using long exposures for those, but for anything in the deep sky, that's when you've really got to, it's so faint that you have to do long exposures. And that leads to a few issues that you have to solve. And of course, there's also the dedicated, but a lot more expensive, dedicated astrophotography cameras, which come in both CCD or CMOS. CCDs, I believe, in the amateur lines are really hard to get now because a lot of the dedicated cameras now are using CMOS sensors. And the CMOS have got better over time as well in terms of their sensitivity. Basic, this is really basic, don't take this literally, but your photons come in, hit the tiny sensor, which is probably only a few microns across. Typically, what's a typical DSLR sensor is about 3 or 4 microns, the pixels in.
Yeah, depending on the
Depends on how big the sensor is and how many, the resolution of the sensor. In a way, the bigger the pixel, it's easier to store more electrons in it, and also it'll gather more light because it's covering a slightly larger area. So there's pluses and minuses to having high resolution versus a lower resolution, but lower noise, more sensitivity with astrophotography cameras. So effectively what happens is you expose and expose until the pixel cell can't hold any more information. It either starts overflowing, which is called blooming, and it overflows into the adjacent pixels, or else they have what they call anti-blooming, which stops that, but it means you can't get any more data. That's basically fully exposed. Same thing happens with ordinary photography. They call it having blown highlights. In other words, your bright sky or sun or whatever in the picture is just completely blown out. There's no real information there because the pixels are recording maximum. Okay, so all of these sensors are actually not color sensitive or don't have any color information. They are sensitive to all the visual and a little bit either side as well. So they'll be responsive to infrared and ultraviolet light. And so the signal coming out of one pixel just tells you how bright whatever it was looking at was. Doesn't tell you any color information. So there's two ways you can get around this with consumer color cameras, or there's some dedicated astro cameras that have this as well. You have what's called a mask of color filters over the top of the sensor. So this particular arrangement here is called the Bayer filter arrangement. If you expand out the array, you notice there's actually more green pixels than red and blue. So when your camera converts it back to an image you can display, your raw processing software, it understands that and figures out how to approximate human vision when it's converting the raw file to something you can actually see on a screen. So a lot of cameras, of course, astro cameras don't, but consumer cameras convert the raw data internally. If you ask them to, you can tell it that to shoot JPEG or HEIF or whatever other format. So the camera is actually doing the conversion to something you can actually view internally. But then you're stuck with whatever the camera manufacturer thought was good. So generally for astrophotography, they won't have designed your processing for that. So you better get the raw data off the camera before you do your own processing rather than use the files created by the camera, JPEGs or whatever other format. So with an astro camera, which is a monochrome camera like that Flea one I was talking about earlier, what you do is instead of having this mask over the sensor, you just take multiple images with using different colored filters. And this is an example how this can be done using a filter wheel. You have these round filters that slot in there, and it's just a carousel, and you select whatever filters you want for approximating human vision. It would be red, green, blue, and maybe alpha luminance, which is no filter. And then you can combine those in software to form a color image. But with these, you can also use scientific filters or narrowband filters that are pulling different information out of the scene. Another thing that I already alluded to with these digital cameras is you get what's called thermal noise, sometimes called dark current, and this limits how long an exposure you can take. That's dependent on the temperature. So if you're on a cold winter's night, you can probably get less noise than you would going outside in the summer.
Yep.
Dedicated astro cameras actually have a built-in chiller to get around this, and they might, typically amateur ones might go to minus 20 centigrade, something like that. There's another kind of noise as well that you get on a camera, is that when you actually read the data out of the sensor, the actual electronics add a little bit of noise, and that's called readout noise. And that's an inherent property of the chip, that whatever chip they have and the electronics are using, that does the readout before it's converted into an actual digital file. Once it's in the form of a digital file, in theory, there should be no more changes to the data or loss of data, except when you convert it to JPEG, which is a lossy format. ISO invariant means, if you're familiar with what ISO is on a digital camera, it's basically how much you amplify the signal. And it's the idea of it is it approximates the old film days where you could buy ISO 100 film or ISO 400 film, and the ISO 400 was more sensitive, but it was also more grainy and a little bit similar for digital, except that you actually can dial whatever ISO you want. And some of them allow you to dial ridiculous ISOs like 50,000 or something like that.
Yeah.
But if you do that, you'll notice the image is very noisy. But you might need to do it if you're in a dark inside scene or something. The cameras spit out raw files tend to be proprietary formats. So depending on which sort you've got, ARW Sony is that right?
Yeah.
The CR3 is a Canon RAW, and NEF, what's that, Fuji or something like that? Nikon. Oh yeah, and Fuji will have their own proprietary format as well, but most of your processing software can read these and figure out what to do with them. If you've got a dedicated Astro camera, it will normally spit out data in using the FITS file format, Flexible Image Transport System, which is not proprietary, so it's doesn't not encumbered with any copyright issues. I mentioned all this already about the consumer cameras will process the raw file into some other kind of format that your computer can display directly. But we tend not to use those for astronomy. Okay, methods of using your camera. You can use combining with your optics. You've got afocal projection. What this is what happens if you go up to the Zeiss and put your phone on the Zeiss eyepiece. The technical term for that is afocal projection. You can use prime focus, where you take your lens off your camera if it's got a removable lens, adapt it directly to the telescope, and there's no other optics other than the telescope and just the camera. That's what's called prime focus astrophotography. You have negative lens projection. You know, that sounds a bit strange. Why would you do that? Basically, what you do is you intervene a Barlow lens in between the telescope and the camera. And anyone guess why you do that?
Uncle Ed.
Oh, he's giving the show away here. So particularly if your telescope had say a 1200 or 2 meter focal length, the smaller Smith Cassegrains. If you want to take an image of a planet like Jupiter or Saturn, again, the image is going to be quite small. So you use Barlow lens, basically acting as a magnifier, if you like, to make the image scale bigger. So that's the reason you do that, generally just for planetary photography. And then there's eyepiece projection. And I might have, this is basically just a scheme showing you how it's working. So the top one is the basically afocal, where you've got an eyepiece in the telescope. You attach the camera or hold the camera over the eyepiece in the film plane at the end there. Then eyepiece projection is slightly different. It's where you still use an eyepiece, but you take the lens off the camera.
Can you see Ganymede or any other moons, like its moons?
Yeah. If you take images of Jupiter, you can see the moons as well.
What about Enceladus?
You'd need quite a big telescope. That's quite a small moon. Generally, with an amateur scope, you'll probably only pick up the major moons.
Okay.
Yeah. So prime focus is pretty obvious. You have no optics other than the telescope optics. and then the negative lens projection with a Barlow intervening. Okay, so one of the problems we have is how do we hold the camera or the telescope? Handheld is possible maybe, but not generally advisable on a long exposure.
For moon it'll work.
Yeah.
But anything other than the moon, probably not advisable.
Yeah, so fixed camera and tripod, great for taking star trail pictures, because you want your camera in a fixed position and really steady, and you might be taking hundreds of images over several hours, and you don't want the camera to move at all. So that's pretty essential for that kind of thing. But also, even if you're tracking the sky, you need something like a tripod with some kind of tracking mechanism on top of it. What I mean by that, well, if you're familiar with tracking telescopes, you come with two sorts. There's the alt-azimuth type, where they can drive the telescope like a lazy Susan around the horizon and an altitude up and down, and those can be computerized so that they track the sky. You're still going to be limited to how long an exposure you can do with that, because an effective field rotation, and I'll explain what that is shortly. But if you have an equatorial mount, you're basically just following the rotation of the Earth, and so you can basically, if the alignment is really good with the South Celestial Pole in this hemisphere, and the mount is a really good mount, you can basically track indefinitely.
How can you see Mars?
Sorry?
How can you see Mars?
You can see it with just with your eye.
What about Phobos and Deimos?
Difficult. Again, you need a big telescope for those.
Yeah.
Okay, so an example, you can just with a equatorial tracking with a camera and lens, you can get what are called Sky Tracker, I think is one of them. Sky Guide is a slightly more heavy duty one.
The Society does have a sky tracker.
Yeah.
And it's a YouTube video.
Which you can rent. I actually have one myself, a Sky Guider, which is a slightly heavier duty one. But for the equatorial tracking to work, you have to polar align, which is can be tricky.
In the southern hemisphere, anyway.
Mm. So untracked imaging, there's what they have this so-called rule of 500. So if you were taking a wide-angle image with a lens and camera, what you do is you take the number 500 and divide it by the focal length of your lens. So let's say you're using a really wide-angle 14mm lens with a full-frame camera. Then you divide 14 into 500, and that tells you how long you can expose for before you'll notice the star movement. I mean, if you pixel peep, you can see it earlier than that, but you can probably get away with that length of time, maybe 400 if you're finicky. And if you've got a crop sensor, then the time is even less. So probably use the rule of 350 or something like that.
Yeah.
Yeah. But of course, as mentioned, if you're wanting star trails, then you don't care about this. Okay, this is trying to explain what field rotation is with an LTAS mount. And if you think about it, our head is on an LTAS mount. So when we're looking at the sky, we turn around that way and we look up and down. And so you can see the image there of the constellation Leo. And I'm looking at it at a certain time of night, and I have to tilt over like that to sort of line it up with Leo. Wait an hour or two, and it's crossing the meridian, and now it looks as though it's see how it's turned. And then wait a couple of hours later, it's gone past the meridian and it's turned more. And the exact same thing happens in the eyepiece or on the sensor of a telescope. if you're tracking an alt-azimuth, you'll see that you'll get little streaks of within the image. In fact, if you image long enough, you'd see quite significant star streaks. They'd be arcs.
Yeah, that's one of the first picture Bill showed. That's the star trail.
Yeah, but it's slightly
imagine it
different
that
to a
way.
star trail because in this case you are actually tracking the sky,
True.
but you're effectively rotating the camera as you go.
So,
And so, in fact, this is the way the big professional observatories work. They actually do have this field rotation problem, but what they do is they actually unrotate the whole camera. So they have a mechanism among the motor that negates this field rotation. And it really has to be computer controlled because you can see the formula there underneath. The field rotation is quite complicated. It depends on your altitude and your the azimuth you're looking at, and it depends where you are on the Earth. So your observer's latitude matters. So the computer can do this formula and negate the field rotation. You can get amateur devices that'll do this as well, but the thing is, you stack in another device, it's something else that can break down or go wrong. So probably, unless there's a real reason for it, you're probably better to use it if you want really long exposures to just use an equatorial mount. Okay, one of the big bugbears of astrophotography is focusing, because the camera autofocus, not really. I don't know how good the latest AI assisted ones are, but whether they know that they're looking at the night sky or that kind of thing. But generally, you're better off using manual focus with a DSLR type of camera or a mirrorless camera. You can normally bring the scene up on the live view and magnify it. So typically you can go to 5 or 10 times magnification, wind the ISO right up and look at a bright star, and then do a manual focus adjustment on the lens until the image on the live view is as small as possible, and start off maybe at 5 times and then go to 10 times to do the final focusing tweak. I think that it's pretty good for wide angle lenses. That sort of scheme isn't so good for telescopes. It sort of does work, but you'll never get really spot on focus doing that. So you can use 2 other methods. You can use a focusing mask, or you can do it in software if you've got a computer connected to your camera. So this weird looking thing here, you can print these out and cut them out or whatever. There's on the internet you can download patterns for these. You could manually cut them out of a thin piece of black plastic or something with one of those little what do you call them, box knife kind of thing, if you're patient enough. And you'd think, oh, why would I do that? Well, this is what happens when you put that over your objective as you're moving the focuser through focus. See the 3 lines? So you adjust your focus until you get that perfect pattern of those lines just as they're coming in here. You'll see them.
Yeah, cross.
Bang. So there's your perfect focus. That one is called a Batinov mask, named after the inventor. I've no idea how he came up with that scheme, but
That kind of looks like a supernova. Yeah.
And if you've got a computer-controlled camera, you can bring the images back and live to the computer. The computer software will analyze the image of a star, and you use this method. It's called full width at the half maximum. So you can see where the maximum intensity of the light curve is. And what you do is you try to, at half the width, you want the maximum possible intensity. So you adjust your focus. Generally, the width will reduce to a certain point, and if you go beyond that, it'll start to go blurry again. So the computer will tell you, or you can have a computer-controlled focuser as well. Yeah, I think most of the software have this. Any of the capture programs, SharkCat would have it. I know there's some software you can get that are specific for DSLRs and mirrorless cameras, and they have software that will do this on your computer. You connect your camera up to the computer, so it's controlled by the computer rather than by the shutter. Some tips. So shoot RAW, and fine if you do RAW plus JPG, because you might just want to have a quick look at your single shot images. The RAW images you have to process. Okay, as mentioned earlier, lower ISO means lower noise but longer exposure. And there's a theory that some cameras have what they call ISO invariance. I think it was mentioned before that you can take a exposure of a certain length of time, and the ISO actually makes no difference to the data captured because the same amount of light is falling on the sensor. And as long as the circuitry isn't doing anything weird with the processing, the actual available data should be the same. But not all sensors behave in that way. So something to be aware of. With a DSLR, you definitely want to turn on mirror lockup. Usually, if you know how a DSLR works, you don't have this problem with a mirrorless camera. But when you're looking through the viewfinder on a DSLR, you're actually looking through the lens, and it uses a little flip mirror so that you're looking through the lens. When you press the shutter, the mirror flips up out of the way and lets the light through to the sensor. But the problem when you do that, if you're doing long exposures, that actually causes a little bit of vibration, and you'll get a little bit of jitter at the beginning and end of the exposure. So if your camera will do it, tell it to lock the mirror up out of the way. It means you can't use the viewfinder, but you generally don't anyway with astrophotography. And obviously, the other problem is if you press the button, you're again shaking the camera. So you don't want to do that. You want some kind of remote shutter release, either a software one or one of those ones you put it on bulb mode and you press a button. Or you can buy electronic devices that can be programmed. What do they call them? Intervalometers. Yeah. The reason you'd use an intervalometer, some of the more modern cameras actually you can program them to take a series of exposures, but they usually probably limit the length of the exposure. I know my camera refuses to take an image of exposure longer than 30 seconds. So I have to use an intervalometer to put it in bulb mode, and if I want to take a 1 or 2 minute exposure, 2 minutes at least, or 3 minutes for star trails. Otherwise, you just get too many images and you get a huge amount of data. So obviously cameras that have articulating displays are quite handy because you can, depending on where your camera is positioned on the mount, you can tilt the display so you can see what's going on at a convenient angle. All right, a little bit about processing. Obviously, with those wide angle shots, you don't need to do stacking. You can take a single image. And I think there was a guy we had as a VHT lecturer a few years ago from Iran who does a lot of the nightscape photography for National Geographic. Can you remember his name?
I'm trying to remember.
But he swears he thinks it's cheating stacking. So all of his images basically are single shots. And if you see Tafreshi or something like that. Somebody.
Tafreshi.
Yeah, that's right. Yeah. He says that it's not the real thing if you're stacking multiple exposures. So he was very good at what he did. It's still around, I believe.
National Geographic doesn't allow any processing. So.
Oh, right.
Really?
Yeah.
Oh, okay.
I guess they don't allow composite. Yeah.
Yeah. Well, that's the other thing with a skyscape. You can use a sky tracker, track the sky to use a longer exposure of the sky, but that's going to blur the ground. But you can take another shot of the ground and then basically make a composite image. So you've got a sharp ground as well as a sharp sky. And there's no problem doing that, but you should always own up to it, particularly if you're entering the competition. You explain to them this is a composite image of, that kind of thing. And AI enhancement is definitely not allowed in competitions. So some of the programs you can use, the ones listed at the top there, Deep Sky Stacker, Cirrel, Registack 6, Auto Stacker 2. They're free. Those are free programs. Deep Sky Stacker is pretty self-explanatory. You'd use it for that purpose, for deep sky imaging. Cirrel is a multi-purpose one.
Yeah.
It's a lot more sophisticated than Deep Sky Tracker, but there's probably a much bigger learning curve. You have to run scripts and stuff to get it to do things. Cirrel is cross-platform, so it's available in Mac, Linux, and Windows. I think the other two, Registacks and Auto Stacker, are Windows only.
Yeah, most of them are Windows.
Yeah, those ones are what you are really aimed at planetary stuff and lunar stuff, where particularly for stacking solar system type images. Some people actually prefer Auto Stacker to do the processing of the movie if you're doing a planetary movie. And then what they do, they transfer the output of Auto Stack into Registack 6 because it's got a really amazing sharpening algorithm. So for bringing out the final detail. And then if you want to go the paid route, you can use Maxim DL or the rather amazing program called PixInsight. And that's a program with a major learning curve to figure out how to use it, but it's probably the one that the real serious people use. Specifically for star trails, there's some other options, and specifically designed for star trails when you stack them. But those other stacking programs, what they do, you give it, say, a stack of 100 images, they throw out the bad ones if they look blurry, and you can tell it sort of, you can give it various criteria for selecting, or you can just go through the images yourself and say, oh, that one looks good, that one's blurry, chuck it out because a cloud passed over or whatever. But for star trails, I recommend the Star Stacks program, or there's another one called Sequitur, which is quite good at this as well. But the thing I like about Star Trek Stacks, it's got a little cheat in it, because what happens is when you take multiple digital images, if you stack them with most programs, when you zoom in, there's a tiny little gap, and that's the gap between frames, because there's a finite time between ending one frame and starting another one. So what Star Stacks does, it actually fills in the gaps, kind of cheating, but makes the image a bit more aesthetically pleasing. You don't have to stack the moon. Yeah, single shots are usually fine, but there's still an advantage because you'll get atmospheric effects that'll slightly blur things. So stacking is still worthwhile doing on the moon just to get a really sharp final result. And planets, though, are really small, so you need a long focal length. with the Zeiss telescope, we don't need to use a Barlow lens with that. You've got a focal length of 6.6 meters, which is enough for the planets generally. And as said, you take a movie rather than individual frames. With DSLRs, what I've found is the movie mode of generally is not going to be any good. But that's not the case of the really modern ones that have got really high res like 8K or even 4K movies. It's a bit different for those modern ones. But the older ones might do 1080p is the best they can do. And that's not good enough for getting planetary images. I found this program called Backyard EOS because I had a Canon camera. There's a Nikon version of the software. And what that allows you to do, it allows you to record the 5 times live view. From what I've read, when you're actually displaying on your live view screen, when it's at 5 times, the pixels on the live view display are actually 1-to-1 with the sensor in that mode, or they happen to be with Canon cameras.
Yes, fine for that.
It may not be the case with other ones.
Yeah.
So what Blackguard EOS does, it just records the live view as a movie, and you get really good planetary images that way. So if you've got, I think the Nikon one has a similar scheme where the software will handle that for you.
Also, many of the modern camera actually has that built in. They just take the
Yeah. Oh, yeah. You can just take a crop, and if it's a sensor that can do 8K or 4K, then you've got plenty of resolution there already in the sensor.
The pixel size is still bigger generally on a DSLR though.
Than a webcam. Yeah, because webcams are not designed to getting they're not for pretty picture type stuff. They're generally like used for surveillance or that kind of stuff, and they have a really small pixel size usually, and that's really good for planets because you can get down to the theoretical resolution of your telescope.
A cell phone camera would actually be technically, if you could have a cell phone camera with no lens,
it would be nice.
that would actually be ideal for it.
The actual if you probably voids your warranty, but you could extract the camera. In fact, that's another thing that some people do with DSLRs. They decide, they want maximum sensitivity, so you want to remove the Bayer filter from the sensor, and there are people that will do that for you. But I suspect if you took the camera back to Nikon afterwards, they probably wouldn't get the warranty for it.
Yeah, we'll go through a lot of effort for this.
Okay. I already mentioned this. You want lots of detail, a Barlow lens or eyepiece projection. And for this, auto stack 2 and registacks are good for that purpose. Okay, just a wee thing on theory. You want to know how much detail can you actually get out of your telescope. Well, it's got nothing to do with magnification because the magnification is created by the eyepiece. What limits the resolution is the size of the lens or the mirror, the main mirror. And a guy called this is called the Rayleigh criterion. So if you looking at a particular angular resolution, take the sine of whatever, like 1 arc second or whatever. Sorry, you evaluate the number on the left, which is 1.22. You can read up about where on earth that number comes from. The wavelength of the light, so maybe green, will be typical for human vision. Divide by the capital D is the diameter of the mirror or primary objective lens. And then that will tell you in arc seconds how small you can resolve something.
Mm-hmm.
So obviously, just looking at it, the shorter the wavelength, you can resolve better. So blue light will resolve better than red because the wavelength of red is longer. But the bigger D is, the better you can do, the more you can resolve. But in practice, you hit a problem with if you happen to be on the Earth, because the Earth's atmosphere throws this formula out the window because the atmosphere is moving around. And we talk about seeing. Probably the best seeing we'd ever get in Auckland is about 1 arc second. So if your telescope can theoretically resolve 1/10 of an arc second, well, you never get that unless you go into outer space or top of a really high mountain. And so this is how they kind of work it out. The image of a star is shown at the bottom there, and the image of a star is this kind of diffraction pattern, and actually only the central spot is the Airy disk, and then you've got the diffraction rings around the outside, and they get fainter as you go out. You're more than just the 2 that you see there, but the third one is pretty much almost invisible, even on a image. And you see what happens as the objects you're imaging get closer together, it gets harder and harder to tell them apart. And so this formula is worked out so that you can just tell that there's 2 stars there rather than 1. So that's the limiting resolution. Obviously, imaging stars, you don't really care about this. Maybe binary stars, if you can separate them. But this is sort of detail on the moon or planets. So basically, the bigger your objective is, or your primary mirror, the more you can resolve in theory, provided your optics are good quality, of course. A little bit about processing. Most of these programs, well, all of them really, you can give them as well as the images you've captured. You can take what are called calibration frames, and there's a number of sorts of those. What's called a bias frame. What you do is you basically put a cap over your lens, set the camera to take the shortest possible exposure, like, I don't know, whatever it is, 4,000ths of a second. And you take maybe 16 of those, and that's what's called a bias frame. That's used to measure the readout noise of the sensor. And also it tells you the sensor doesn't start at 0, there's a little offset. And so the offset is not perfectly even over the whole chip. So what the bias frame is measuring is that offset plus the readout noise from the sensor. Why do you want this information? Because you can end up with a cleaner image if you give this information to your processing software. And you've got what are called dark frames. So what you do is if you were taking a 1 minute exposure and you've done 100 exposures of 1 minute of your object, you want to then take a series of what are called dark frames. Again, you block the light from the sensor with a lens cap or whatever, and then you have to, with a digital camera, you have to have the exact same settings that you took your light frames, same ISO. On the bias frame, the ISO you want to be the same as well that you're going to take your images with. Same, ideally, should be the same temperature. That's not always possible because the temperature drifts around and that. But the idea of the darks is you take a series of images of nothing, but for the same exposure length as your actual pictures. And this is measuring what's called the dark current of the camera or the thermal noise. These frames, because they should have no data on them, it also picks up what are called hot pixels. And they're faulty pixels in your sensor that always read out the maximum value. So they're basically crook. And I'm pretty sure that unless you pay a lot of money, pretty much any sensor will have a few of these.
You felt like
because I think the manufacturers have they can have no more hot pixels and no more than a certain number of dead pixels, but there's probably going to be some, unless you're really, really lucky, get a perfect sensor. Okay, the flat. So what this is, in your optical train, there's going to be dust, maybe a fingerprint or something, or you've got vignetting because some of the light is getting blocked before it reaches the sensor on the outside parts. So the flat takes care of all these issues. What you do is, one option is to actually image the evening sky after sunset, but when the sky's still bright, and you take an exposure to typically about half maximum. So you don't want to blow the thing out. You want to take a long enough exposure so that the pixels are roughly half full, and that's called a flat. And this caters for the optical train, also variations of the pixels, because some pixels might be slightly more sensitive than others. So your flat can correct for that, can correct for dust and other optical defects. And obviously, if there's a black spot in your flat, then that's a dead pixel. So that's how the software can figure that out. The way you can handle this is use what's called dithering, so that in your light frames, you just slightly off, if your mount can do it, you can tell it move a bit to the left, bit up, bit down. So between each frame, you slightly move the sensor. And what that does, it means that the hot pixels and dead pixels won't be imaging the same spot in the scene, so the software can actually eliminate those from the image. So that's a technique called dithering. That's about all I wanted to say. If you've got any questions? If not, go out and start imaging. Yeah, no.
I got this one question that did somebody land on any of the major moons of Jupiter?
So what? I didn't quite catch it. Something about moons.
Somebody land on one of the major moons?
No, that hasn't been done. Done yet. It actually has with Titan though. They did land a probe on the surface of Titan. I don't think anything's been landed on any of Jupiter's moons so far, but there is a plan to do that.
Okay.
Yeah, isn't there a mission plan coming up? Did they actually land on the surface? No. I think there's a plan to do it, but it hasn't been done yet.
Yeah, not yet.
I've got a question. So you talk about biases and darts, and we've got stacking.
You don't have to do that. The stacking programs will let you just stack lights, but if you're going for the ultimate quality, and it seems pretty tedious, you present the program with your flats, your bias frames, your darks, and the actual images, and it does some magic computations and spits out hopefully a really good image at the end.
It's an amazing thing, and it's I guess the question I have is, if we fast forward 20 years or even 10 years, and let's say smart telescopes, things that they're doing right now.
Oh, I think so. I think some of these
do you think
some of these do that already. Like these digital telescopes have got a lot of this stuff built in.
Yes,
They do automatic darks and that kind of thing.
That's what I mean. Is like, is there a point where maybe all but your semi-professional photographers are going to say, this is easier. I don't have to pre-process. I don't have a polar alignment.
It's definitely an easier entry point.
Yeah.
There are limitations because you're not going to get a Rolf Olson image out of a digital telescope,
At the moment,
or in fact planetary images, because those so far they haven't come out with one with really long focal length and large aperture. But if they did that, that's going to be a very expensive device.
Yeah.
Anything else?
Like the dwarf and stuff, they already do the so they come out of the factory, like it'll tell you if you don't have the dark frames in the right temperature and the right settings, it will ask you to take it. Otherwise, you just
Yeah.
recycle it. And I think it does come stock with like the biases and stuff already. So
Because they can
are
probably
already
measure that
using
in
it.
factory,
Yeah,
so
they
they
are
know,
already
you know.
doing it.
It
And
does feel a bit like cheating, but at the
Yeah.
same time, there's something about opening up our
oh yeah,
hobby to a huge number of people.
it's so much easier to
Yeah.
use. I've been playing with one, so it's fun.
And as we said earlier, the society is in the process of buying one for the rental stock. So if anyone wants to have a go with it, you'll be able to loan it. If it's really popular, you might even buy another one.
They are a lot of fun. But yeah, try to get you to spend more money.
Yeah, I've seen a number of
Proper
people put
system.
their images on Facebook, and they
Yeah.
get pretty nice images out of them.
Yeah.
Oh yeah, no.
Another question about astrophotography. I just wanted to remind, especially the new members here, that our library, which is behind that wall, through that door by the exit, is open, and our librarian is here. Next time, if you want to rent out a book or DVD and so forth.
There's periodicals there, but I think you meant to only have the periodicals for a week. But the books is a month. Or are you fairly lenient?
I just say bring it back. I just might want to look at them, but I don't worry about what they're cracking.
Okay.
And also, I didn't open the door site, so I don't have my key. So
It is open.
Oh, thanks for coming along, everyone.
Right.